Yeah, right. Good. Thank you for pressing the record. Right. So this week we're welcoming Tony Linero from University of Texas at Austin, who's going to talk about how ignorability is actually an informative prior, especially in high dimensions, I think. So over to you, Tony. Thank you.
All right. Thank you for thanks for the invitation. I'm very happy to be here. And yeah, so if you have any questions in the as I step through, I'm happy to take them as they go. Or how long was this? Is 50 minutes? Is that right?
Yeah, roughly 50 minutes, and then we can have more questions at the end.
Okay. All right. So yeah, so I think that I'll just start with kind of the main point of the of what I'm trying to say, just so that if you can take one thing away from this talk, I'll be happy if we sort of agree on the following point, which is that in causal inference settings, so typically for causal inference, you're worried about essentially confounding, right? I have some causal effect that I'm trying to estimate, and the fundamental problem is that things are confounded, and I need to somehow do something to control for the confounding. But in high dimensional settings, if you're doing Bayesian inference or even regularized frequentist inference, priors implicitly often will encode the belief that there is no confounding on average. And so what this is a figure. There is some measure of the amount of total confounding in the estimation of a causal effect. And what I have as you go from left to right is changing basically the number of dimensions or the number of confounders that you're controlling for. And your prior implicitly believes something about the amount of confounding, right? So the amount of confounding is a parameter of your model. And as you increase the dimension, basically the prior believes more and more that that confounding is not a problem, which is sort of the opposite of what you actually think typically. If you're doing causal inference and you think the problem is non-trivial, you don't believe that confounding is not a problem, and therefore you should not use a prior that does something like this. So in terms of practical consequences, what this typically will lead to is estimates of average treatment effects that are highly biased. And so it's kind of this, I mean, you're trying to do your best in some sense, right? You think there's a lot of potential confounders and you're trying to control for them all. You're trying to be responsible. And somehow the prior is kind of accomplishing the opposite of what you want it to. It's more and more entrenching the belief that confounding is actually not a problem. So this is the main point. And if you kind of understand this point, then you understand that there's sort of other things you need to do. It's not as straightforward to apply, say, Bayesian machine learning or machine learning methods in general. So this is true both of high dimensional problems with many covariates, but it's also true if you try to do some sort of non-parametric adjustment. And this is, I think, I'm not the first person to have noticed this type of phenomenon, but it's not, I think, as well known as maybe it should be, because you occasionally will see people making these sorts of blunders in practice. So the questions I'm going to try to deal with are, one, how can you go about diagnosing these types of problems? So basically, when should I expect a phenomenon like this to occur? If I have a problem that I'm interested in, how do I know that this is potentially happening? What can you do to correct these types of problems? So once I've identified it, how do I go about fixing it? Or are there any kind of standard tools for fixing it? And lastly, and hopefully I'll get a chance to talk about this, but can you characterize sort of settings in which either you know for sure that this is a problem that you're going to need to deal with, or there may be some situations where you can get away with doing something that maybe, that maybe this doesn't happen all the time. Like maybe there are some settings we can identify in which I'm sort of shielded from this type of behavior. So I'll make a couple of pitches for why we should sort of care about it. Okay, it's some theoretical issue, maybe not. It happens in practice to us, but the selling points are basically trying to avoid these types of traps in high-dimensional non-parametric problems. As kind of machine learning methods become more in vogue, and we try to leverage them. The predictive successes of machine learning. How can you sort of avoid these types of issues? And generally things are quite bad. If you fall into any of the pitfalls, the results basically you won't get good estimates of whatever it is that you're trying to estimate. So it's important to be kind of cognizant and do something causally responsible in a sense. This is a more theoretical talk than I typically will give, and so I feel compelled to justify myself before diving into the, kind of the technical points. My main methodological track of research is in Bayesian nonparametric methods. So building basically big flexible models, and generally I'm trying to estimate causal parameters. So I'm interested in building big models and using them to estimate causal parameters and quantify uncertainty. I think that the things that I'm going to say have methodological implications, but for the most part, this talk is not going to be on any specific set of applications. It will be kind of general. And so I'd like to take a couple of minutes to talk about some successes of Bayesian nonparametrics in practice to kind of justify why I think this is kind of, these are objects that are worth studying, or phenomena worth studying. So one point that has kind of come up in the causal inference literature relatively recently is a recognition that certain Bayesian nonparametric methods perform very well in, well, you can't ever tell with a causal inference method, whether you're getting the right answer or not, because you don't observe the outcomes under both the treated and control group, right? You need to observe both potential outcomes to assess whether you're doing something that is recovering the truth well. Nevertheless, there's been a push towards trying to design these realistic simulation settings where people basically submit their favorite algorithms and they try to see, okay, how do they actually do? When we know the ground truth, how do these things actually do? And they try very hard to introduce realistic amounts of confounding and realistic amounts of heterogeneity. But a consistent trend in that literature, or that in these studies, has been that a particular method called Bayesian additive regression trees, which is a Bayesian nonparametric method, seems to do very well relative to competitors. So basically, if you take Bayesian additive regression trees, or this algorithm called the Bayesian causal forest, you will tend to get estimates that are quite good in terms of covering causal effects. So this is a coverage for the average treatment effect on treated. And basically, BART methods that are suitably modified will attain, nothing actually does particularly, nothing is exactly bang on 95% coverage, but they do quite well at a good deal for the length of the intervals that you ultimately end up getting. And they tend to have quite low root mean squared errors and interval lengths as well. And they seem to consistently do better than various other competitors. In particular, if you're thinking of tree-based methods, there's a competing method called causal random forests that they seem to do quite well against. So these methods seem to have a reputation in the causal inference, or a growing reputation of being like pretty effective. And somewhat surprisingly, also there's an uptick in the use of these methods to do science. So a couple of papers, one published in Nature, right? Definitely not a methods paper, but like an example of these methods being used in, ostensibly serious science. So this is using a Bayesian causal forest to estimate heterogeneous treatment effects in education. And also applications in a variety of other settings. This particular one using Bayesian causal forests for inferring heterogeneous treatment effects related to medicated abortions. So these they're kind of increasing in popularity, and so the stuff I'm going to talk about is not completely disconnected from these strands of research that are going on, and the results I'll talk about do apply more or less directly to the methods that are being used. So with that justification of myself out of the way, I'll start with just basic background in causal inference. So what are the presumably, if you've done work in causal inference, all of this stuff will be basically review, kind of obvious stuff. I wouldn't have to explicitly tell you, but if you're not, this is sort of the setup and notation I'll use. So I have a causal effect, or I have an outcome of interest. Right, the yi's will be an outcome if unit I receives exposure level A. So I have find potential outcome yi of A. Cap A is going to be the exposure that unit I actually receives. So I sort of have two. I have yi1, yi0. We'll just focus on a binary treatment. And so I have two potential outcomes. And I will have a set of confounders that I'm measuring xi. So I have xi set of confounders. And there's two important quantities that you have to estimate if you're estimating things non-parametrically. There are various methods you can use to try to estimate causal effects, but they will invariably involve estimating one of these functions: the propensity score, just the probability of receiving treatment, condition on my confounders, and the outcome regression function, or the response surface. Basically, what is the mean of the observed outcome, conditional on both treatment and the covariates or confounders. So if you know at least one of these, you'll be able to estimate the causal effects, or at least average causal effects. You'll be able to estimate, not even estimate. I mean, if you know these, then you basically know the causal effect for the most part. So yeah, we'll need to generally construct estimators for these things. And just for concreteness, this is a setting that I've sort of looked at in my own applications. You could say yi is medical expenditure if you either smoke or don't smoke. AI could be smoking status, whether you smoke or not. And X could be things like BMI, propensity to engage in risk-taking behavior. Because if people take risks, maybe they are less likely to incur medical, they're maybe likely to ignore medical issues. And age, things like that. So things that are predictive of both the outcome and the exposure. And we'll make these three assumptions, very standard assumptions, and I won't revisit them. But just to we'll need to make these assumptions to make any progress. One is the stable unit treatment value assumption, which is just the potential outcome for unit I treatment that is received by the other units. So, the effect of smoking on your health doesn't depend on whether I smoke or not, which actually is, there are settings where that sort of thing doesn't make sense. In that specific case, there's the issue of secondhand smoke, but we'll just assume without question that this is true. That justifies the potential outcomes only depending on my exposure, which is already assumed implicitly on this slide. Assume consistency, which is that the outcome that I observe is just the potential outcome process evaluated at the observed treatment, which could either be taken as a definition, but I think the intention behind it is that there's not multiple versions of the treatment. At least that's what seems to be communicated by listing this as an assumption. And lastly, you assume positivity, which is basically everyone can get treated. If there are some subpopulations that never receive treatment, then you're going to have problems estimating causal effects within that subpopulation. So those are the assumptions, and we'll start with sort of the very basic, simplest causal inference question you could ask, which is, what is the average treatment effect? So I define parameter psi, which is just the average of potential outcome if I'm treated minus potential outcome if I'm not treated. And I'll start by revisiting why is this a non-trivial? Why is this non-trivial? Well, one reason it's non-trivial is that I don't observe both of these. I don't observe people with both under both the treated and control condition. But that's not precisely what I mean by why is this non-trivial. There's another way, even if you didn't observe both of these, there's other ways the problem could be trivial. The main thing you need to control for in these problems is the existence of common causes, right? So basically the existence of confounders. So if I have a common cause, if there are no common causes, so let's say there are no common causes of the outcome and the treatment, then it will be true that the expected value of the potential outcome will just be the expected value of the outcome conditioned on observing that exposure. So we could estimate this second piece non-parametrically fairly easily. Either if A is discrete, just average outcome in the treated group, outcome in the control group, and subtract them. Even if A is continuous, you could do some sort of smoothing. So problem is trivial if there are no confounders, and in which case you're basically reverting to essentially a randomized study. So when there's no confounding, you can form this very simple estimator, which is just the average of the treated minus the average of the control. And it's a very, very good estimator when there's no confounding. So, if you knew there was no confounding, then you would probably use this estimator. I mean, there are tweaks to it. Maybe you could still use covariate information in various ways, but yeah, you would be in great shape. And now here, this is the step where you have to kind of make the logic is maybe backwards of what one would typically think, which is that a priori, if you're doing causal inference, you don't believe this is a good estimator. So as a representation of your subjective belief, your prior is that this is a bad estimator. Otherwise, you wouldn't be controlling for confounders in the first place. And therefore, you should reject out of hand any priors that actually implicitly encode the belief that this is a good estimator. So yeah, if your prior believes that this is a good estimator, it is a sign that it doesn't conform to your subjective beliefs, and it should be rejected because you don't believe that this is you don't actually believe this is a good estimator. There's a couple. So I had a question in the chat. Why 0 means we... Oh, okay. I think it was asked and answered. Okay. So yeah, before proceeding, could this actually happen to me? Could I actually use a prior that does this? Because maybe you think that you could only specify such a prior if you're incompetent in some way. And I would argue the answer is yes. The reason I would argue the answer is yes is that I can give you examples of people doing this. Otherwise, people that I respect, people that are otherwise clever, I've seen walk into this trap. And I don't really want to call people out. And just to preserve my social relationships, maybe I should be more willing to. I'll talk about a source of such bad priors in a few slides when I go through basically the history. But yeah, I don't want to slander anybody by calling them out specifically. So there's another related question, which is this specific to Bayesian inference? So all the arguments I'm making is very Bayesian flavor. Is it like unique to Bayes, or if I'm frequentist, am I going to encounter some variant of this problem? And so the answer again is yes. It's just that basically you have to change the framing a little bit, which is that instead of there being a prior encoding belief that the amount of or degree of confounding is close to 0, you instead need to frame it as your regularization method, whatever you're doing to regularize things, is implicitly going to shrink your causal effect estimators towards what I was calling kind of the stupid estimator, just difference in means of the treated and control. So you can inadvertently end up shrinking towards bad estimators if you want to think about it just in terms of regularization. This has been referred to as regularization-induced confounding, which is terminology that was introduced in this paper on Bayesian causal forests, which really kind of takes the regularization viewpoint of what I'm talking about. Yeah, there's a discussion, extensive discussion in this paper on Bayesian causal force if you want to see how this applies even to kind of machine learning methods in general. But there is a long strand of research in what I call non-naive machine learning based methods that don't do this, that basically use insights from semi-parametric and good estimators. They're generally not going to fall into any of these traps, which are things like targeted maximum likelihood estimation, double machine learning, and methods along those in those veins. So methods for constructing doubly robust estimators aren't going to typically bungle themselves into these situations. So part of the reason I focus on Bayesians is I think there's less of a tradition in Bayesian work of kind of thinking in terms of what is semi-parametrically optimal, and trying to convince them that actually they should probably start caring more about these things than they do, because it's too easy sometimes for the religious Bayesians, at least, to reject frequentist arguments out of hand. Maybe they shouldn't. Okay, yeah, so this has still all basically just been mostly background. So I'll actually now talk about where these problems are kind of coming from. So I have a model, define theta to be beta and phi. Beta is going to parameterize the outcome distribution, and phi is going to parameterize the propensity score distribution. So y will follow some density, y given x, and then a just propensity, random Bernoulli, and two set of assumptions. So I'll call it Bayesian ignorable if two things hold. The first is the typical no unmeasured confounders assumption, which is we say a prior model pair is Bayesian ignorable if first the potential outcomes are independent of the treatment given the confounders. So no unmeasured confounders. So you need to make this assumption, right, to have any chance of estimating causal effect. Well, I mean, there are alternatives, obviously, but you need to have some assumption of kind of this level of severity to make to estimate causal effects. And the second is that the prior factors in this particular way, which is that pi beta phi is the product of pi beta and pi phi. And the payoff for the second one is that it simplifies your modeling assumptions, and it's very often made. So there's causal inference world. There's also missing data world, which kind of hinge on similar sorts of identification problems. And factorizations in the Bayesian literature in missing data world are very common. They like to basically assume missing at random and then some ignorability assumption on the prior. So there's prior factorization, because it makes it really easy to do a lot of things, to basically impute missing data. So yeah, we make these kind of two general assumptions. If you make those assumptions, then the average treatment effect is identified through this thing called the G formula. So there you can get the marginal distribution of your potential outcomes basically through standardization. And the second thing that falls out of this is posterior independence, which is that the posterior distribution of beta doesn't depend on the selection model, or it doesn't depend on the exposure model. And this is just, application of the likelihood principle. Those drop out as proportionality constants. So a selection mechanism is, there's two uses of this word ignorable. One is, the ignorability assumption in causal inference. The other is ignorability of the selection mechanism in the missing data sense, which is basically that you don't need to model the missing data mechanism. So people don't like this latter property, or it's been pointed out that it has some kind of nasty implications. There's two conflicting observations. One is that prior independence implies the propensity score is ignorable, but there's a bunch of frequentist results in theory that says, no, you really should be controlling for the propensity score. So sort of what is actually going on here. So example is that imagine the ideal setting in which the propensity score is known exactly. You could form a Horvitz-Thompson estimator and get a root-n consistent estimator of the causal effect fairly easily. But methods that try to learn nonparametrically without using the propensity score, such a root-n rate is going to be to be infeasible. So there are good frequentist estimators that make heavy use of the propensity score, whereas there's fairly simple Bayesian argument that if your prior satisfies this assumption of factorizing, then you're precluded basically from such estimators. It seems to commit you to using bad estimators, which is kind of strange. So this is discussed in a series of kind of remarkable. Well, there's initial most of I think this observation I attribute. I mean, possibly I guess this sort of thing is known before this, but there's a famous paper by Rubin and Ritov that makes this point, I think, fairly forcefully, and then a remarkable exchange between Jamie Robbins and Larry Wasserman with Chris Sims, who's a Nobel Prize-winning economist, that debate this sort of fact extensively. And I mean, as another thing, I hope that you take away from this talk is to read and engage with these posts, because I don't know, at the time when I read them, it was kind of shocking to me, and it seemed clearly that Robbins and Wasserman won the debate from my view, and I don't have a good answer to a lot of the things that Robbins and Wasserman say, but a lot of the stuff that I'll talk about is very much attributable to things that sort of Chris Sims was saying in this particular debate, wrapping it around in some additional mathematics. Okay, so now actually, what is kind of the technical parts of this? So I'll introduce this thing that I call the confounding bias parameter and discuss the prior distribution on this parameter as a source for rejecting essentially this prior factorization. So define the confounding bias parameter as the difference of the mean if you just condition on the observed treatment and the mean of the actual potential outcome, right? And so this is the thing you're trying to estimate, and the thing that you're kind of the naive estimator. So the naive target parameter, if you'd like. So delta A is a measure in some sense of how confounded AI is with YI on average, and if this parameter is 0, then the estimator, kind of the naive estimator, is going to be root n consistent and will have all these nice properties. So, but this is a parameter just as any other parameter, right? It's a function of the parameters, and so it makes sense to talk about what the prior believes about this parameter. And by way of a specific example, this is a variant of the Bayesian causal forest where I've just taken the Bayesian tree-based methods and replace them with Gaussian processes. So I have some outcome, have a prognostic effect of the confounders. I have a treatment effect. So tau is the heterogeneous treatment effect, and Gaussian errors. And these type of methods are quite good, I think, at inferring heterogeneous treatment effects in practice. And so maybe we just place a Gaussian process prior on these and just sort of see what happens. And we have this explicit definition of a confounding bias parameter. This is, by the way, just what a picture of a Gaussian process looks like, in case you're not used to seeing such things. Just a prior on function space, kind of random functions that you could use. And this is what the prior distribution on this looks like. So I'm going from actually fairly small amounts of confounders, 5 to 10 to 20. And very, very quickly, the prior actually concentrates exponentially fast in the number of predictors, the prior belief about the degree of confounding. And so this is referred to as called prior dogmatism, that the prior dogmatically believes that there's no confounding. Despite my efforts to control for more confounders, my prior actually doesn't believe that confounding is such an issue. So why should you expect this to happen? Well, it's a combination of sort of two facts. One is that if you take independent random vectors in a higher infinite dimensional space, then it's just a fact of high dimensional geometry that such things are probably approximately orthogonal, right? If you take two random vectors and you look at the angle between them, they're basically going to be orthogonal. The second fact is that the confounding bias is basically an inner product of these two things. So for basically all the models, you can characterize the confounding bias as an inner product between the parameter indexing the outcome and the parameter indexing the exposure model. So if confounding bias is an angle between these, and most random vectors are orthogonal, then the confounding bias should concentrate around 0. And consequently, in the particular case of this process that I defined, you can write the confounding bias parameter as a covariance of mu and phi. And so this is going to be an inner product with respect to a particular it's going to be the inner product of these two quantities with respect to a particular inner product. And therefore, you should just intuitively expect that the confounding bias is going to be approximately 0 if you don't encode prior independence. So to add a little bit more, I mean, this isn't such a big deal, but in the specific case of this model, you can basically show that the confounding bias parameter is Gaussian with a variance that goes to 0 exponentially as you increase the number of predictors. So this is problematic. And it's not a feature of the fact that I use Gaussian processes, right? This is just to illustrate the example. But if you do anything else, like if you use BART, Bayesian additive regression trees, if you use Dirichlet process mixtures, anything like that, you're not a model change away from fixing this issue. It's sort of fundamental. Okay, so second toy model is this case of ridge regression, high-dimensional ridge regression. So we imagine that y is related to the outcome through this model. And just to make the model a little bit easier to analyze, let's assume continuous treatment now, both following this kind of linear regression with Gaussian covariates, and gamma is the causal effect. And again, you can explicitly derive this selection bias parameter. It's again determined by an inner product between the model parameters. And again, you should find that that for such a model, for a naive ridge model, you should get concentration of such a prior on the selection bias around 0. So you can do a little bit more in the case of ridge regression and try to quantify what the effect of this is. So I do engage in what I call an average case analysis, which is basically specifying a random effects model to understand the bias that arises in the setting. So assume high dimensional setting, not ultra high, but predictors scaling with the sample size, Gaussian distribution for the confounders, and then these IID kind of ridge priors for phi j and beta j, where to induce a non-trivial amount of selection bias, I add this offset to the betas. So this is a generative model that we'll use to study what happens to the ridge model, but it's designed to induce substantial selection bias and kind of make this parameter delta, the selection bias, not concentrate towards 0. So if you're in a setting where this doesn't concentrate towards 0, what should you see happening? And this is basically equivalent to needing to control for some measure of the exposure, basically throwing the propensity score in as a predictor. Again, you'll have this prior concentration, which is this from the first slide. As you ratchet up the dimensionality, you'll get concentration. And it's possible to explicitly derive the limiting bias under this random effects model. Has this sort of form that, fully explaining what this bias term looks like would require a digression into random matrix theory, which I don't particularly want to do. But the main point is that the degree of, in addition to the fact that this bias exists, it's determined very strongly by the spectrum of the covariance of the predictors, which is a hint at what at where you might be able to avoid these problems. So, and it turns out that the spectrum or the distribution of the covariates matters quite a bit. And it will turn out that if you have high degrees of collinearity in your predictors, that can be one way to avoid it. Basically, if a lot of your features are redundant, then you sort of won't necessarily run into these types of issues. But yeah, you do get asymptotic bias, and this is what this bias basically looks like, is for various settings of both the aspect ratio, which is basically what is the ratio of p to n. These are kind of going down on the x or down on the y-axis as you go from north to south, and then different values of the ridge parameter for these. So this bias from the previous slide is given by these blue lines. In the orange line, there's a correction, a corrected version of this, which does much better, but it basically amounts to controlling for a point estimate of the propensity score in the estimators. So doing something like that and kind of adaptively estimating the amount of regularization to use can lead to basically unbiased estimators, at least for this average case model. So the way that you can kind of not have this happen is rather than writing down a prior and just sort of hoping that you will encode a good prior for delta, is to just start with the prior on delta and kind of go from there. So rather than hoping that we'll have a good prior on delta, we'll just directly specify the prior on delta, and that goes a long way toward basically fixing it. So yeah, short story is that basically you're going to need to control for the propensity score. You're going to need to induce some sort of dependence between the propensity and the outcome, which is generally good practice anyway, right? So if you're in the habit of doing this, this is yeah, you're not guaranteed to be safe, but you're kind of in good shape. Simple way to do it is, if you're modeling a function non-parametrically, is to plug in a non-parametric function of the propensity score as a covariate. In which case you can show that the magnitude of the bias is going to be dominated by the covariance between the non-parametric function of the propensity score and the propensity score. And so this generally is not going to concentrate near zero, as long as you, if you model this G function flexibly, or even, I mean, you could just set G as 1 over the propensity score, and that would give you like sort of an estimator that's in the pushing towards doubly robust. But it suffices to just control for a non-parametric function of it. So you can do some simulation. This is a simulation directly taken from this Bayesian causal forest paper of Han et al. Some model for propensity score, model for outcome and treatment effect. It has heterogeneous treatment effects, but we'll just go for estimating the average treatment effect. It's a bunch of different things that I consider. One is doing Gaussian process regression in a way that doesn't correct for the propensity score, and then a variety of methods that basically amount to different choices of G. So you could take G to be the inverse function, which is just controlling for the inverse propensity score. And you could also drop this B term, and you could also model this non-parametrically with splines. So I can either spline the propensity score, I can inverse the propensity score, and I might or might not include an additional Gaussian process regression on at the end. These are the results. So when the dimension is 5, and I have root mean squared error, coverage, estimated standard error, and empirical standard error, when you're in dimension 5, actually things seem okay. The main thing to pay attention to is this naive estimator that doesn't do anything. Has pretty good root mean squared error, has reasonable coverage, and relatively low standard errors. But by the time you even get up to 20, which is, I think, a fairly typical setting, controlling for 20 confounders, if you haven't done anything, then basically coverage drops to 0, root mean squared error is astronomical, and you have very misleading estimates of the standard error. So your estimated standard error is only about 0.5 on average, but the actual standard error is much higher. So really bad outcomes if you're just in this not doing any kind of correction. And then revisiting ridge, a simple way to fix it is to just again drop in the propensity score, and as a predictor, estimate the propensity score. In which case, again, you're not going to get this concentration of the selection bias parameter towards 0. And again, you can do various simulations and show. Okay, so in blue here is the behavior of naive ridge. And then there are various other corrections. So there is this correction based on the Robin's transformation. And then there's this other correction that I'm proposing, which is just drop it in as a covariate. The propensity score is a covariate. And either of those corrections works fairly well. The naive kind of, in most of the settings, unless the naive model happens to be true, you'll get bad coverage. You'll get misleading interval widths, and you'll get very high root mean squared errors. There's a slight preference for this business of adding it in as an unpenalized covariate, the propensity score, over using this other method based on the Robin's transformation. But it's sort of a very slight improvement in terms of the operating characteristics. The main point is that with you just use ridge, your coverage falls off a cliff and your root mean squared errors go just diverge. So lastly, I'll wrap it up, and I'll probably finish a few minutes early. When can you expect that this issue does not occur? Because evidently sometimes people do this and are not immediately punished. So are there any circumstances in which such failures do not lead to any problems? And I'll say that if you're interested in this, I have a paper it's like accepted a few days ago, so I'm feeling happy about that. But you have a few seconds to grab a screenshot and pull up the paper. But basically, there are two loopholes that you can sort of escape through, where you sort of don't have to do anything to get automatic correction. One is if you have a setting in which the confounders are highly dependent. So if you have what I mean by high dependence is, if I rewind here, distribution of the confounders, if their covariance matrix is close to singular, if it's nearly a singular matrix, then what turns out will happen is that the ridge prior will sort of automatically use a kind of matching method to be able to estimate things. So one loophole is just near singularity in the distribution of the covariates. So that's loophole one, and then loophole two is if the beta and phi, if they depend on high dimensional predictors, but there's some kind of common sparsity pattern, that this is an alternate way to bypass this kind of issue. So there's never any penalty. There's no downside for implementing the controls that I described. You shouldn't ever, I think, count on these things happening for you. But nevertheless, it's useful to know when maybe you have less things to be kind of concerned about. And so I'll just close with a simple illustration of this fact, which is a setting in which I have a high dimensional latent factor model, in which the dimension of the latent factor is actually is quite small. So the xi's don't lie exactly on a low dimensional hyperplane, but they're sort of close to it. They deviate by this term sigma x from the hyperplane. And so if you have a really good latent factor model, meaning that this sigma x is really small, then you'll tend to get estimators that are just as good as if you controlled for the propensity score. And I have a bunch of other empirical results along this line that basically show more generally if the xi's concentrate on a low dimensional manifold, then you can get away with ignoring these prior dogmatism issues. Okay, well, that's really all I wanted to talk about. So as far as general recommendations, it's definitely enforce dependence between outcome and propensity score models. Don't use pure outcome regression models, which I think was already bad practice, but definitely don't do it if you're tempted to do it. There are a couple of ways to do this, right? You could specify a joint model for the propensity score in the outcome model. There are some drawbacks to doing this. There's this phenomenon of model feedback that basically, if you misspecify one of the models, then it can kind of corrupt the whole thing, which you don't want that. But there are easier ways to do it, which is to use this kind of awkward prior, where you have the parameter beta not depend on the propensity score, but by the actual design. If you have the beta depend on the design, then it's easy and kind of retains all the benefits of this joint model. But more generally, and this is sort of I think a general issue for people who are trained in Bayesian methods, is there's something inherently about Bayesian methods that skews you toward kind of thinking about things in the average case rather than the worst case. But the average case is the average with respect to the prior that I get to write down. And generally, one should think about what aspects of a problem make the problem difficult and start designing the prior from that standpoint. Make sure that your prior in general for whatever problem you're working on doesn't accidentally imply the problem is easy. Because I think it's very easy, and this extends beyond causal inference, but it's really easy to write down priors that secretly think this subtle problem that you're interested in is actually super easy. And if the prior thinks it's an easy problem, it's going to use sort of a silly estimator of the thing that you care about. And all these problems extend to other more exotic designs. So this pops up in mediation analysis. It pops up for estimating conditional average treatment effects. It pops up in basically every kind of problem in causal inference. All right, yeah. So that's all I wanted to say. And yeah, thanks for your attention.
Well, thank you very much. If imagine here a very loud clap from all of us in the room. So if anybody has questions, yeah, please feel free to raise your hand. Joanna, you've raised your hand, so go ahead and unmute yourself.
Hi, thank you very much. Very nice, very interesting talk. So I've used BCF quite a lot, and in fact, we have a paper where we added sparsity using your Dart prior instead of the BART prior.
Right, yeah.
Separately for tau and nu. And one of the things that we spent ages doing is trying to force the propensity score to stay in the model by adding very high weights. And ultimately what ended up happening almost all the time in the examples is that it just really wanted to drop out. Do you think that comes down to maybe phi and beta? I mean, having common sparsity patterns that made that happen. Our interpretation was that the nonparametric prior is adjusting so well that it no longer needs that one-dimensional summary. But do you think that what should be done, I suppose?
That certainly could happen. It could be the case. So yeah, there's multiple explanations. One is that your outcome model is really, really good. In which case, yeah, some of these, right, another way for these things not to happen is for you to be awesome at modeling things. And so a setting in which you expect to really need that propensity score. I mean, I guess maybe this is the folklore of BCF, that things tend to get hairiest when the ground truths aren't well approximated by the functions that you're using. So things that trees find hard to estimate can kind of exacerbate the issue. Yeah, I mean, it's also hard. I mean, especially if you're studying something with a high dimensional predictor, Yeah, it's hard to say without kind of looking at sort of specifically what's going on, but yeah, there are a few things that could be happening. But yeah, one could be that just it didn't need it. I kind of feel I would get a little bit uncomfortable if I saw that happening, to be honest. Well, no, so you also did enforce a common sparsity pattern. So that could also be right. If you're saying you're enforcing common sparsity pattern between the propensity score and the outcome, that yeah, that could definitely make it so that you don't need the propensity. You don't need to control for the raw propensity score anymore.
I mean, it wasn't. We didn't in the simulation. We tried different things, but in real data, I suppose sometimes there is a natural similar pattern sometimes, right?
Yeah. I mean, that's the idea.
Propensity.
Yeah, there has to be on some level there has to be a similar pattern, right? If you don't believe there's a similar pattern, then again, it's sort of this: is the problem trivial or not? Like there has to be some shared pattern in some sense. That shared pattern could be shared sparsity pattern, I guess, is like specifically what you're looking at. Yeah.
Well, thank you. Very nice talk.
Good, thank you. So Udita.
Thank you, Dr. Linero, for your wonderful talk. So my question is about one fact which you have used in this article. It's about that in the higher infinite dimension, phi and beta are orthogonal. I mean, approximately orthogonal. Is it a? Is it we can use it like a theorem, or it's a fact, or we have assumed that?
This is so I don't, it's funny, I say this and then like when I try to actually find to me this is like a textbook fact, like it's the curse of dimensionality. I don't know that I would call it a theorem. Right. Just, I mean, it instantiates itself in various ways throughout statistics, so like there's the fact sometimes to positive effect, like if you if you can pick random design matrices for fMRIs or things like that, then the fact that high dimensional random vectors are nearly orthogonal can be used to like improve estimations when you have things as sparsity. But yeah, I don't know, like a book on high dimensional statistics, I guess, should reference this kind of fact. It's like random directions on a sphere are all in high dimensions are just but I didn't state the precise fact because there's all these caveats, and right, there are caveats, which is what is the distribution you're talking about, and if your distribution concentrates these on like a low dimensional subspace, then it's not true anymore. So it has to be kind of an honest high dimensional space in a sense. I don't know if that answers your question, but
yes, I mean, I am just asking the question. And also the confounding parameter delta. First, you are telling that we don't have to assume any prior belief. So first, we have seen that the parameter delta, it concentrates around 0 by taking the high density. So I mean, after some calculation, you have shown that it's now not concentrate around the 0. So, I mean, you were not assuming the prior assumption that our confounding on an average is not so much have any effect.
Yeah, so I introduced basically added some extra parameters to force that to not happen. So if you, sort of if you have the expression, I guess I'll talk about this. So this only concentrates near 0, basically, if beta and phi are independent a priori. So if beta and phi are a priori independent, then you'll have this concentrating near 0. If they're not independent, then who knows? And one way to make them not independent is basically to center beta in the direction of phi, which is what where is it? Which is what this prior is sort of implicitly doing. It implicitly is centering beta near phi and kind of forcing it to. Yeah, probably I should have added more details on what exactly is going on here, but it turns into this kind of expression, which this is no longer going to concentrate near zero because right, the issue is sort of as p diverges in this formula is that this term in the denominator grows like p, and the term in the numerator goes like the square root of p, and so hence as it goes to zero, whereas over here the both of the terms are growing at the same rate, and so it kind of doesn't concentrate anymore.
Thank you.
Good, thank you. I have a question, and then I'll ask my question first, and then I'll allow Owen to ask his question. So, okay, so I understand that to remove this regularization bias, we need to sort of bring in this dependency back. But the pragmatic approach that is advocated in BCF is to sort of basically use the propensity score as any other variable, right? And sort of put it potentially in a non-parametric form there. But that doesn't account for the uncertainty properly, right? I sort of on a first stage, like estimate my function of the exposure, and then I pretend that I knew it from the beginning. It seems to not be a proper Bayesian thing. I understand that the proper Bayesian thing is not going to work because of the feedback. So what would be a better solution?
Well, okay. So all right. There are a few comments here. One is okay. It's not non-Bayesian. So you can write down a joint for everything for which this is the right thing to do, controlling for the propensity score. It's just that the prior is a little bit weird, but it is like I don't know, right? You're having your beta depend on your design, which is like an allowable thing to do. People do it with the G prior all the time, and for some reason, no one takes the issue that the design is random, as people seem to be happy to use the G prior. But yeah, to your point, yeah, I agree. I think most people find this a bit suspicious. Now plugging, I could go ad nauseum about whether it's actually a good idea to drop it propensity score in the outcome regression function. That feels to me slightly dangerous. I haven't hashed this out with the BCF people, but I would tend to want to put it out as like a spline or something out at the end, but you know, whatever. There's many ways you can do it. One way of accounting for uncertainty. So if you're worried about uncertainty in the propensity score, one thing you can do is add multiple estimates to the propensity score. So if you have a whole posterior from fitting propensity score model, rather than just plugging in the point estimate, you could plug in quantiles of that. So you know, so that's kind of like a very I don't know, it's a hacky way to add in uncertainty. So maybe I throw in not just the point estimate, but the 25th percentile and 75th percentile to capture this notion of including uncertainty in the propensity score. And I haven't seen anyone do that, but it seems like something that someone could do if they were very worried about accounting for uncertainty.
All right, thank you. Owen?
Thank you for a great talk. I will try and be very fast. Sorry about that. I was struck by the cases where you could think about your delta parameter in a fairly geometric way. You've already mentioned again inner products and angles between them. Your belief is that this delta parameter should have a nice spread to start with, because it's unreasonable to think that it's near zero. Given that in some cases there's a fairly straightforward geometrical way of thinking about delta, is it possible to reweight priors in those settings in order to effectively ensure that they are behaving in the way that you would like them to?
So reweighting the prior, I guess I think I'm missing the...
Well, no, in a naive way, I suppose, if you've sampled from your priors for whichever parameters it is, the beta and the phi's, let's say, and then you can downweight the samples that have delta near zero and upweight the samples. But presumably, because of the geometrical interpretation, you can probably do this analytically, I guess.
Okay, no, I hadn't thought about this. So taking a prior and doing some sort of reweight, like yeah, I don't know. I haven't thought about this. I suppose there's many ways, I guess, of trying to upweight it, or you know, ways to try to correct it. Maybe I should meditate on what you're saying and try to see if there's something maybe smarter that I could be doing to force it to be sort of more diffuse.
Thanks for a great talk.
Indeed, thank you very much, Tony. So we've run out of time, but we had a good discussion, and you gave us an excellent talk. And thanks once again.
All right, thanks for having me.
All right, then, and the rest of you, see you next week. Bye now.